Whenever you are measuring something, the measurement system itself is actually quite important in how good your results are going to be, not just of the measurement, but also of your process itself. Hello, I'm Tom. Welcome to my channel where we talk about continuous improvement in an industrial setting. And today's video is sort of a small overview of how can we test and improve the measurement system itself. So at any point when you are stabilizing a system, you are doing statistical process control, you are doing improving your CPK, you are working on the stability of a line and on a process, you should also take into account that the measurement system you are using, and in fact any measurement system you are using, is not going to be 100% accurate. Now it's an unfortunate given, right? No matter how much you calibrate, it is not going to be 100%, but you can get very close to that 100%. And there are some basic rules on what you need, and one of them that you may have heard before is that in MSA, and especially in R&R, which is repeatability, reproducibility, you want your measurement system to have no more than 10% of the variation that you observe in the total process to come from the measurement, and so more than 90% from the process. Very nice. But then how do we actually get to this? Now, we won't go into the details of these tools, but I'll give you a bit of an overview of what you want to do when you are checking, so analyzing your measurement systems. So first off, there is an important concept to realize. There is, and it's almost like a bit of Aristotle, but there is the truth that we don't really know, right? So there is a specific truth in our process. That is our aiming circle that we are trying to hit. Now, the black dots here are measurements that we make and how close they are to the actual truth that that product should have. And you see the top left, spot on. It's very nicely centered and they're all in this bullseye of our target. That is an absolutely perfect, well, as perfect as we can get it, measurement system, because every time we get the value that the truth also gives. Now, what can also happen is that sort of on average we are hitting the middle, so it's very nicely around the middle, but it's very broad, right? So there's a lot of spread in what we hit, what the measurement system tells us. The truth is still the little bullseye in the middle, and you saw one of them actually hit it, but we've also got values left and right, top and bottom. Now, the good thing is that such a system is centered. So if you just aggregate enough values, you get an average, and you can say, well, the average of all of these is still here. And this is something that, for instance, statistical process control can use. It can use it pretty well as long as it's not too extreme. But also many quality systems can sort of use this, because you say that there is spread in your system, in the process itself and in the measurement, and we take into account that there is a certain level of spread. So we're not going to do anything with one measurement result anyway. We're going to wait for 8 of them, for instance, and then we get a nice average, and based on those patterns, we say, well, it's going well, or hey, look, they're all outside, so we have to do something. So, but that, it still is a measurement system that is really not perfect, and in a specific way, this system is not accurate. Now, there is another thing going on. When we go down, what you can also see is that whoever does the test, whenever you do the test, if you retest the same part the next day, different technician tests it, you get the same result every time. These are very tricky, because the thing is, you now have a very strong reason to believe that here is your factual center, while the truth is still over there. So this is not on target or not precise. It should have been here and they are there. And then you've got both of them, so your and way off center and the spread is quite big. That means you're not precise and not accurate. Now that is just to get a general way of talking about the problems we have in a measurement system. And there are basically three tests. So the Kappa test, the RNR, and calibration. That's not really a test, but it is part of a system where you also test and then correct. And two of them, Kappa and RNR, they can manage this spread within the measurement results. And I think what is also good to understand, I didn't say it with the targets yet, but these lying pretty far apart, that does not mean that we have parts that are very different. We get different results for the same part, right? So the truth really, it has to be like that one. We get different results, different operators doing the test give us different results. A different time of day gives us a different result. Pure chance gives us a different result. But on average, okay, they will average out in the middle in this one. Now, to do this left-right split, right? So the accuracy of our measurement. So the accuracy part, we are going to check. We're going to check specifically what if two people, two systems, or three or four, but what if several people check the same part? Will they get the same result? Well, will they all be at least equally wrong or equally right instead of having this spread? Now there are two main ways of testing this, and those are the Kappa and the R&R analyses. Those are the bread and butter of measurement systems analysis. And when do we use them? When we have a system where you have either good or bad, so a pass-fail type of system, then we use the Kappa analysis. And that is because with Kappa analysis, what we basically do, and there are two main ways of doing it, but it is you get the first person to say, well, these are good, these are good, these are good, that one's bad, good, bad, bad, good, bad. And then you hope that the second person who's also looking at exactly the same product, but a bit later, of course, right? They don't communicate. Will also say good, 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 bad, bad. And you hope that they say exactly the same, because then you have got a nice test that pinpoints them the same at least, right? So accurately. Now for that, there is this there's this table that you draw. So at Kappa analysis, what you basically do, and this is the standard way of Kappa analysis, is you check if person A said it was good, then you also check for the same part what did person B say, and if person A said it was good and person B said it was good, it'll get into the top left. If person A said it was bad and person B said it was bad, it will get into the bottom right. A says it is bad, B says it's good, it comes over here. A says it's good, B says it's bad, it comes over here. Now, what you want, of course, are these two, top left, bottom right, because then both of your testers, they are in agreement. That is basically what you want. This is what you don't want. And now there is some formula to check how big are the chances, knowing that there are so many good, so many bad ones, how big are the chances that those two people just randomly choose the same, and how did they compare, they do compared to those chances. And if you get a zero value, that is just like chance. In fact, it can go to -1. -1 is if it is completely 100% over there, so they are completely away from, well, on the wrong side from chance, but you never get that basically. So pure chance, 0 is about the lowest you can get, and then 1, you basically get it when everything is in these two. Right? That is a 1. Everything in between, there's this scale, if there's 1 or 2 or 3 in those other quadrants, you go down and you end up at 0 at some point. And what we're trying to get there is to have, well, at least a 70–80% on this test. That's not 70% good. There is a formula for it. Go check it. It is going to be, that requires a video all on its own. Now, then there is, what if we can measure something? So we're looking at it, but it's not good, bad. It is now becoming, how big is it actually? We're measuring a length, a weight, even a color scale, but anything that has a continuous value. And we like these types of measurements a lot more, really. I mean, if you are in quality management, you might really like this good, bad, so the pass-fail type of condition, which is nice because it tells the operator what to do. But when you are checking the measurement system, always try to go for this one. So very often what we also have is up until a certain measure it is still good, and beyond it it is wrong. When you're doing measurement systems analysis, get that raw data. So don't get the pass-fail, because to do a kappa analysis in a good way you actually need a lot more measurements than for a good R&R. So do the continuous scale measurement, right? So to do that weight or that spectrophotometry measurement, the intensity of the light, so not the good, bad, but really the plate count, the weight, the whatever is behind the pass-fail. But for this one, well, I can draw them out also a bit, but you hopefully already know, because they are some of my most popular videos, the RNR method, right? When you've got this operator A, B, and C, all testing 10 at least products 3 times, and what you then do is you compare it, and you're really going to look at, those operators. If they test something a couple of times, do they get the same result? So the first thing, what we're going to check, the repeatability, is it's sort of, we just look at one operator. We will do this for all 3 of them in the calculation, but we're going to look at this one operator and say, if they test part 1, are they going to get the same value 3 times? If yes, we've got a good repeatability. This person can repeat their own measurements. And of course, the different parts, they should be different. They will have different results. But that part, so part number 7, should have 3 times the same value. Now, the second part you do, the reproducibility, is can one of the other operators reproduce the same values? So we're also going to check this average with that average with that average. We're going to see if it matters who is operating the measurement device, or what day it is, or even which measurement device it is. Because we just have one measurement system, we want them all to hit the same target. So it shouldn't matter if we have a different laboratory or a different person or a different measurement device, if we're trying to measure the same thing. And here it looks like, these were 20 values in total, although they were measured twice, right? So that's 20 for A, but also 20 for B. Here we seem to have a lot more, because it's at least 10 pieces is quite common. 3 times, so it's already 90, not 40, but this also tells you a lot more. So you can do this with slightly lower numbers if you really need to, but do it with the 10, 3, 3 as a sort of minimum, so 90-ish. It'll give you a lot of information, because it will not only tell you how the spread is, it will also tell you if it is, because even the same operator with the same machine cannot reproduce it, or that there is a difference between operators, and you can use this test quite easily to check between laboratories. All of this, if you set it up correctly, you can also check between devices or between laboratories. This one also, you always compare 2 measurers, so 2 people or 2 machines. There is a way, and Paul Allen actually explains it quite nicely, there is a way where you first have an expert panel set what is the real, right, the true result, and then you score people against that. That is also a way. You are still formally checking one-on-one, because you're checking the expert to your test operator every time compared to that expert, but that way you can make a very nice comparison. Now, R&R will compare against the whole population that you take. So all of the tests that you put in, they are used to make the average. That also means that, and especially the standard way of Kappa and this RNR, do you now also see why it will not tell you how precise you are? So if we are indeed in this situation where we've got almost the same results, no matter who does the test, they're all here, you will get brilliant RNR results, because your RNR will say, yes, we can repeat and reproduce our measurement. Your Kappa will say, yeah, they are in absolute agreement. What is wrong, what is right, which passed, which failed. They are, unfortunately, all off the mark. Now for that, we use calibration. And the easiest way to show calibration is by having scales, for instance. Now, if you are in a company working with any weight balances, scales, things like that, especially if they are for commercial use, what you will know is that you will have them calibrated, at least yearly. Somebody will come by, it might be your own internal quality department, it might be some state authority that will come by with very expensive but very precise weights, and those weights are the truth. Of course, it is also questionable, but they have a very good way of keeping them. So those weights are going to be as close to the truth of that weight as you can get. They also internally calibrate that. So you've got the truth coming into your factory. You put it on the scales that you've been using day in, day out. You've been rolling trolleys up and off and whatever, you've been using them. And then you see, after all this use, wear and tear, cleaning it with water, whatever, things happen in a factory. We are not generally very kind to our scales. So in the laboratory, people are generally very kind to their scales, but in a factory, not so much. And you see, does the scale also give the same weight? And you can do it a couple of times, but in the end, if not, you correct it. So you set with different weights, you set how this measurement device reacts so that it will give you again exactly those standard weights that you put on it. And that's another thing, usually you indeed have more than one weight. Now, that is for scales and weight. And it's quite easy, I think, to understand what people are doing, not the technicalities of setting a scale, that's not easy, but what is happening. But this system you can also use in different measurement devices. If you use pH, acidity measurement, you know this because you do it at least daily, right? You have your pH 4, your pH 7 testing solutions. You even automatically calibrate your pH meter. Most pH meters have this function. So they also make this nice line and they have a couple of reference points. But you can also do this on things like taste. Or in fact, that second form of Kappa analysis, where you make one truth by an expert panel, that is sort of calibration as well. Because you somehow have a very precise process of telling the truth. So what is as close to the truth as you can get with measurement and standards, and you usually use way more expensive measurement devices and procedures to get to that truth than would be economically feasible in your day-to-day process. But you can also do that with a pass-fail. You can do it with taste. Is this cheese salty or not, right? So is it on exactly what it should be, or a bit low on the saltiness, or a bit high on the saltiness? You can have expert tasters come in, and preferably not even alone, but with 3 people, set for a number of different cheeses. This one is exactly salty, this one is slightly more salty, this one is slightly less salty. But you set the whole taste pattern, and you do it of course for a couple of different tastes in those products, and then check that with your regular sensory testers. Many people at the quality department, operators, managers, people you invite to your daily sensory. So also that measurement system of sensory, which is generally sort of considered to be a very difficult thing to get accurate, but also to get precise, can be calibrated. Human sensors can be calibrated. The process is the same. You bring in the truth, and then you check if your measurement system gives you that truth, and if not, you start steering. In the case of sensory, that means you start training your people. You start telling them, no, this is how it is, that is how you should rate it. Let's discuss, let's train, let's have more different products. In the case of scales or pH meter, it is much more physical, and you get, this amount of pressure on your weighing cell is 250, that amount is 100, make a nice line between it, and that is how you calibrate scales, but the concept is the same. So it became a bit of a mess on the board, but you have hitting the target exactly, and then when you're not very accurate, you are hitting it on average, but the spread is very big. So small spread, big spread is what you check with this side, Kappa and R&R. Kappa analysis for discrete pass-fail type of measurements, R&R analysis for continuous variable measurements. If you are hitting the target or not, also with a spread, that is the precision of your measurement, and that you do with a calibration. A calibration is something you can do on any type of measurement system, although on some it will be easy, on others it will be harder. I hope that this gave you a bit of an overview where to look. As I said, I explained a little bit of what we're doing here, but if you want to use them, go type in these terms separately. There are YouTube videos, there are Google articles, there is a lot of knowledge on them. But here you've got a nice overview of when do you use them. And if you like that overview, don't forget to hit that like button. Also, if you have any questions about this or requests for another video, don't hesitate, put them in the comments below. For now, I wish you the best of luck with your measurement systems analysis, and as always, don't forget to enjoy the continuous improvement journey.